All right, with that, I think I'm going to go ahead and start the session because we're right at the 15-minute mark. So welcome everybody to Right Sizing, Core Building Material Optimization, where we'll be hearing how to optimize structural elements in order to reduce embodied carbon. For those of you looking for AIA continuing education credits, you can see the learning objectives here on the screen. And we'll be following up after this event with information on how to submit your AIA member number for CEUs. And in the case that we're not able to get to all the questions, we'll ask Duncan and Simon to answer those questions later on, and then we can post those to the CarbonPositive website. I'm sure all of you have heard this by now, but we'll also be posting the recordings from today's sessions to the CarbonPositive website where you accessed this session from. So with that, it is my pleasure to introduce the speakers of the session, and I'll keep their introductions brief so we can get to the content and questions, but their full bios are also on the CarbonPositive website. So to start, Duncan Cox is a senior associate with Thornton Tomasetti and has more than 18 years of experience on a variety of high-profile projects. Duncan specializes in incorporating sustainability aspects into structural and facade designs. He is a leading voice on embodied carbon and life cycle assessment and helped develop Beacon, Thornton Tomasetti's open source carbon counting tool, which, as you heard, they are providing tool demos of today. So if that's something you're interested in following this session, the final one will be, I believe, at 5:30 p.m. UK time. Duncan is joined by his colleague, Simon Cross, a senior associate with Thornton Tomasetti, who has been working within the structural engineering practice in London since 2015. Simon has worked on a number of new build and refurbishment projects and has a particular focus on lowering the embodied carbon of our buildings. And with that, I will pass it over to you, Simon.
All right. Thank you very much. Let me get this all working. We've already had sort of introductions, but say I'm Simon Cross. I work in the structures department in Thornton Tomasetti's London office.
Sorry, I couldn't find my unmute. Yeah, I'm Duncan Cox. I work in sustainability in London as well with Simon. Sorry.
So the title of this presentation was, what is the structural sweet spot for optimizing materials in order to reduce embodied carbon, and are there rules of thumb that we can use in design, or does optimization occur on a case-by-case basis? So what we were looking at talking about in this session was, how do you assess the performance and what's required, sort of carbon budgets and targets, how we can adopt those to then sort of use tools to then sort of at that early concept stage to make sort of decisions, but also sort of looking at sort of back to basics approach. And following that, we'll be taking some specific project examples from a high-rise tower that we're looking at in the City of London, HOBHOUSE, which is also located in London, and a office development for Santander up in the northwest of England.
Okay, so I'm gonna, yeah, so basically I'm gonna talk about where is the problem, why are we doing this presentation. Have I got, oh I do. I've got control, haven't I, Simon? Yes, so sorry. Woof, I need to calm down. You've probably seen this slide in other presentations. I've certainly just showed it in the previous presentation, but I think it's really important that we keep reinforcing this. We have 20 years to get down to our carbon emissions down to zero. That's the basic. From today, we need to get down to zero. If we're not to go past this tipping point of 1.5 degree global temperature rise, it's as simple as that. And so we have a budget, we have a carbon we need to stick to. And when we look at our industry, it's 40% comes from us. And we need to be aware of that and making reductions on that. In the last year, we've seen people are, is this jumping? sorry. Keeps jumping, sorry. In the last year, we've seen a couple of different, we've seen targets starting to be produced to help us get to those reductions. We got Letty that I was involved in, operational and embodied carbon reductions, what we need to be to get to zero. Reba has done some as well. And when we look at that breakdown in terms of operational and embodied carbon, currently with like a building regs compliant building, we're 70% makeup in the UK of our building regs compliant building would be operational carbon. 30%-ish comes from your embodied carbon. If we drive towards this high performance buildings, then we're going to see that shift, and over 50, 60, 70, up to more percent of the carbon will be from embodied carbon in the materials, and even higher if some of these efficient high performance buildings contain more embodied carbon. So we really need to be thinking about it. We've regulated on operational for the last 20, 30 years, and we need to be doing the same on embodied, and we don't have that long to sort of get these numbers down. So I come from a firm of structural engineers, and we realise that we have a big part to play in this. When we look at any building typology, archetype, this is Wimbledon #1 court, we had a look at the embodied carbon in there. 70% is in the structure, the substructure, and the construction of that. That's significant responsibility for us. And it's the same when you look at different archetypes, offices, residential buildings, schools are slightly different because obviously often not as heavily structurally designed because they're a bit more lightweight, but it's still significant. We're still 50% of the embodied carbon is sort of on the structural responsibility, and so we need to look at ways of trying to reduce that as early as we can. From our point of view, what we focus on when you look at the structure and the carbon in the structure, typically 80% of that carbon is in the material choice. It's what materials you choose to design your structure from. We don't, and it's through those materials, excavation and the manufacture of those materials. Our structure doesn't typically need repairing and refurbishment quite like some of the other materials like your M&E, your services, and the facade elements and architectural elements. We do have demolition and transportation impacts, but the big part of the portion is in the material choice, and so that's what we try to focus on. And we do that by upfront looking at doing these structural framing comparisons, comparing. Simon's going to talk a bit more about these later on in some project examples, but we can look at, we're typically on a project at that early stage go, well, what's the options? What are the different materials? And can compare them on different base studies and different arrangements. I want to just make everybody hesitant. This is not one size fits all solution. This was for quite a typical standard sort of frame building. So, but when you look at other options, and we've had evidence of a project elsewhere we're working on in London where we looked for, we use timber because that's always low carbon. It just didn't work because we were trying to apply it to an existing foundation arrangement and trying to do some long spans onto the existing substructure, and the embodied carbon on those long spans in that CLT deck was high, and it came out worse than precast options. So it's important that we do these. We can't just apply these as a rule of thumb for every building because every building's different. We do these upfront studies by some tools we've developed in-house that people are welcome to have a look at and have a play around with. This is ASTERISK, one of them that we've used, where we get a massive model which we can quickly apply sort of our machine learning tools onto massive models to come up with the sort of different structural arrangements depending on the vertical and horizontal grid. From that, we can report back different metrics of efficiency, and one of those, along with cost and volume and material, is the carbon in that building. And these are really powerful early tools for us to look at to get a sense of where the carbon is. And then we can move these into, like, because I mean, these tools are so good at producing so many options and arrangements, but you can get overwhelmed with how you visualize them. So we sort of also build tools. There's another one we look at where we were able to quickly visualize big areas of data and compare. In this case, we were looking at carbon payback over a number of years and when it made sense to put in different arrangements. But these are tools that sort of help us with our understanding of what makes sense and where the carbon is. As we move through, like in the life cycle of a project, we move our tools into different spaces. So we then move from that conceptual side to live reporting tools in our Revit environments. A tool we have here is Spotlight that enables our designers to quickly see in their Revit environment live reporting on where the carbon is, what changes it makes if they changed so the concrete strength and how much is in the foundations, how much is in the vertical structure, and these kind of things. So it's sort of, I always say that carbon is a really good metric of efficiency. If you have a low carbon building, you tend to have got to your most structurally efficient building. It's not always the case, but it tends to sort of be a good marker for our engineers to have. And we also, as recognizing that, yeah, as I said at the start, we've got 20 years to do this. And so just quickly talk about Beacon, where we did this as an open source tool. Does the same thing, quick reporting for engineers in their Revit environment, plugin that will tell you where your carbon is based on some industry averages, GWP potentials that you can amend and adapt. But I am doing a talk on it later, you can come, it's at 5:30. But these are sort of to help that sort of understanding. There are other tools that are in the industry, and I thought worth mentioning. There's Hawkins and Brown. I never know how they say it, Herbert, I think, but that's got more of the building facade and the architectural elements and more of the life cycle stages, a bit more in depth. But once again, it's an open source tool. People are recognizing that we've got to work together to do these things, and so it's that time of working openly and collaboratively. And then also EC3, which is another very powerful tool for you to have a look at, which is a big database of EPDs that you can get different carbon quantities for different manufacturers of concrete, masonry, aluminium, etc. It's largely US field at the moment, but it's easy enough to populate with UK EPDs, and it's a really powerful tool that will compare different product suppliers by others, and the hope is that it creates a bit of competition in the market. Once again, it's an open source product, and we've seen with our with this access to all these tools that we can understand and interrogate our data and understand which buildings have more carbon on and what we need to focus on, and we've been able to show that with these, since we started implementing them, we have been able to seen consistent reductions in the carbon in our building. There's been accompanied with sort of different education streams and stuff, but we can see that these are helping our engineers to make those reductions, but it needs a bit more. And because when you start to understand these buildings a bit more, and when we're looking, like when you start to interrogate the data, we see these overall trends. And like this is from our database of 600 odd buildings, where we're seeing typically carbons in the floors, and that's a good rule of thumb to have. But Simon will show on a project that he's looking at a tall tower in London, that it changes, the shape changes, the carbon is moving, like the predominant areas still in the floors, but there's also a lot more in the walls because it's got big sheer walls carrying the core of that building. And so it's, once again, it's great to have all this access to the data, but you need to look at these projects individually. And again, we can use these to pinpoint where we need to be. As I said, we've got 20 years, and using these lessons from the data we collected, we can see where we need to be in 5 years' time on different building elements if we're to be on track to get to these reductions. Roughly, obviously every building is different, but roughly what's the period of reduction? Can we do that with our structure at the moment? Yeah, maybe we could with certain design aspects, but maybe we don't have the materials. So you start. It's a really good. These are good for understanding how we need to be sort of progressing in the future, and to enable us to get to where we need to be. But what I think is really important, and the most important thing, and I've been involved in this tools development and carbon counting for a number of years, is it's so important to go back to those basics. And I've helped with this document, the embodied carbon primer, and I really encourage people to have a look at it, because it talks about in it primary actions. Before you're doing any of this counting, the numbers are meaningless if you're just going, oh well, actually timber is better than steel. You've got to think more than that if we are to think about getting these reductions to work. You've got to think, do I need to build this? Are there areas of where I can reuse materials? Are there like what are those materials? What's low carbon? What's out there in the market? What really works? And what's this building look like in 20 years time? What's it look like in 50 years time? Can I design for adaptability? Can I sort of load, and some people don't agree with this and it's a viewpoint, but could you load carbon up front and knowing that you're going to increase the service life of that building? Maybe that's not an answer, but one of the most important things is this idea, this thing about building collaboratively. And by that, I mean working with everybody on that supply chain, ingraining in your brief at the start that this is going to be low carbon. This is a driver for where we need to be, because it has to be. And so what we're making sure, we can do these framing arrangements all we want, but if it then gets value engineered out later in the project, then there was no point to doing any of it. It makes us feel better, but it doesn't get anywhere. So it's ensuring that's delivered the whole way down that supply chain. And that's the most powerful thing. The tools are great, but it all comes down to that designing efficiently and designing intelligently. I hand over to Simon now, and he sort of describes some of the projects where he's done that.
Yeah, so as Duncan said, I'm going to discuss some specific real-life examples on projects we've completed or are currently working on within our London office. All these projects have taken some of the principles as discussed by Duncan earlier. Can you reuse? Can you build less? Can you build lighter? Can you build low carbon? Can you build for the future? And can you build collaboratively? These projects are quite different, but we hope that the examples provide a bit of a taster of how we've approached the challenges and how we've implemented the solutions to minimise the impact these buildings have on the environment. So our first example is based upon the works we've completed on a new high-rise commercial tower within the City of London. Unfortunately, this project's still within the early stages of design, so we can't share any further information on it. But what we can share is some of the aspects of what we're trying to achieve. The client on this project has sustainability high on their agenda, and we've scrutinised the design of the structure to minimise our impact on the environment. The ambitions of achieving a low embedded carbon building so high that targets will be included within the planning documentation, which is due to be submitted in the coming months. Clear span flexible floor plates are normally, they're typical for these developments such as this. And in order to achieve the correct balance between flexibility and the amount of embodied carbon, we've studied a number of flooring and base studies to inform the client on their decision. The floor-to-floor heights of the development have also been challenged so that we can also minimise the cladding material within the facade. In addition to this, we've also looked at the core layout, the location and the size, and also its construction, and it's been optimised for the tower. So the extent of the core has been designed to satisfy the lateral stability requirements, with the position located to satisfy the architecture and to minimise the floor areas. What we've been looking at are dual car lift shafts to minimise the amount of material used within the core, whilst still achieving the necessary travel times to circulate vertically around the building. Another area that we investigated was how we could challenge the design life of elements and how the building is planned to be refreshed after 25-year-long cycle. So, for example, the surfaces and the glass might need replacing after 25 years. However, can the cladding be replaced after 50 years? You know, the design of the structure has been completed based on a design of 100 years instead of the standard 50 years. And what we've looked to do is identify what is maintainable and what is lifelong over that design life. So to ensure that our options can be followed through onto site, we've also engaged with contractors early within the design process. This early engagement has provided an insight into how the building can be constructed effectively and efficiently, and that the on-site challenges which our options may present can be achieved in order to obtain this low embodied carbon building. So one of the first studies we completed was the effect on the flooring systems on the embodied carbon. You know, we had to do this in conjunction with all the other criteria requested by the client, such as, you know, requirements for clear span solutions, minimizing the structural floor zones and minimizing the story heights. So this slide indicates some, but not all of the initial studies and options. And, you know, we're showing steel frame solutions with reinforced concrete on metal deck, precast concrete and CLT floor slabs, alongside concrete solutions such as RC flat slabs and post-tension slabs. And they all have their own advantages and disadvantages. For instance, you know, the concrete options do not provide the clear spans necessary, but allow for a shallow structural zone, with services located underneath. And the steel options provide clear spans with an integrated service zone to minimise the depth of that structural zone. So, concentrating on two of the options, you know, although the CLT floor slabs provide the lightest flooring solution, with long span steel options of around 15-16 meters, it created issues with vibration. So to satisfy the vibration issues, we had to add additional mass into the system, and the beams had to be deepened by about 300 mil to achieve the same sort of steel beam tonnages of the equivalent concrete option. Furthermore, you know, we had to look at hard stories of concrete every sort of 3 to 4 floors to satisfy the fire requirements, to create a single compartment over a number of stories, and you know, mixing concrete and timber works on site, introducing the wet trades, and this may potentially sort of complicate procurement routes and construction sequencing. So based upon the studies we completed for this option, the optimum span of these hybrid timber steel structures are probably around the region of about 9 to 10 meters. For the precast option, in order to minimise the wet trades, there's no structural concrete topping has been specified, and what we'd look to do is grout the joints up to ensure that we get the diaphragm action. We detail all the steel work with shear studs and transverse reinforcement, and that would all be grouted in for installation to satisfy the composite action of the system and the code time requirements. We didn't look at the use, or we looked at the use of off-the-shelf precast planks such as Holocore, but we dismissed that early on due to the soffit finish, but at the fact that they don't use any cement replacement in their products and that the units are formed from 100% ordinary Portland cement. So in working with the precast manufacturers and understanding the key aspects and how the planks are produced, collaboratively we've designed this bespoke solution to meet the construction aspirations whilst achieving the enhanced soffit finish and the maximisation of the cement replacements. And as the structures are exposed, the thermal mass of the structure will also be utilised as part of the energy strategy. So in addition to the structural criteria, the sustainability merits of each option were also evaluated for its global warming potential.
Yeah, so just to have a think about what we look at. So we tend to look at 3 different phases in terms of the production. So the manufacture of those materials and the excavation of those materials, or the raw materials, and the transportation of those to the factory, but also the energy flow, the carbon flows from the construction and the material waste, and the transportation of those from the factory to the site as well. There's carbon associated with that, and then, as I said earlier, you also get the demolition carbon as well, and whether you can, what the reuse potential of those materials are. So we look at those 3 phases. If you look at these numbers, you actually see that there's so much more in that production stage.
So although the short span hybrid steel and CLT system performs better in terms of the global warming potential, this needs to be read in conjunction with all the other aspirations of the client. And a balanced approach is necessary to select an optimum solution in terms of the environmental, economical, and social impacts. So for that reason, although the global warming potential is slightly higher, the precast option was selected as the structural system for the flooring. And what we did was we tried to show this in a very simplistic manner to the team, listing the options with a red, amber, green rating based upon the differing criteria. And what we can say is that the highlighted system, the precast, shows that the clear 15-metre spans can be achieved with a shallow structural zone, and although it doesn't necessarily have the lowest embodied carbon, still rates relatively well in comparison to the other options. And using TT's carbon calculator, we've measured the embodied carbon of the structure, about 280 to 300 kilograms of embodied carbon per metre square. And based upon the industry-wide benchmarking from Letty and Reba that Duncan was talking about earlier, we can show that the actions that we've put can deliver a building, ahead, 5 to 7 years ahead of the proposed 2020 targets. So our next example is HOBHOUSE, and HOBHOUSE is located within central London, round the corner from Trafalgar Square, opposite the Sainsbury's wing to the National Gallery, and it's just down the road from Leicester Square. It's a mixed-use development comprising residential, commercial and retail areas. And project goals were many, but centred around the retention, restoration and redevelopment of the Grade 2 listed John Nash building at 3 to 5 Whitcomb Street and the Grade 2 listed basement vaults below the site. Now, the demolition and reconstruction of some of the existing buildings on site also provided benefits for city planning and new public spaces. And the key philosophies of the project was to minimise any structural intervention and preserve the historic fabric of the existing structures. And there are two distinct areas within the developments, which you can see in the photo. The extension above the John Nash building at 3 to 5 Whitcomb Street, and the new buildings above the existing masonry vaults at 7 to 17 Whitcomb Street. So the retention and reuse of the existing structures allowed the lost spaces within the existing structure to be reopened to the public, creating both a positive economic and social contribution. The return of the Royal Watercolour Society, who occupied the site from 1823 for 115 years, have returned back to their original base, and that is a positive success story. There's also been the creation of new public spaces, and the realigned streetscape has regenerated the area. And although the reuse of the structure did impose limitations on the construction of the buildings above, retaining the existing 200-year-old structure vastly decreased the demand for material, the cost and the programme for the construction of an ODU development. And this was estimated to be an additional 9 to 12 months on the programme, the removal of approximately 1,100 metres cubed of additional spoil, and the saving of approximately 350 tonnes of embodied carbon for the construction of any new reinforced concrete elements. We also took a number of positive steps to minimise the impact of the buildings on the environment. So we looked at the reuse and recycling demolition spoil, which was properly sorted and graded on site. We used concrete with a high level of cement replacement, utilised lightweight recycled aggregate, and we've detailed the facade in a manner to minimise on-site wastage, slim it down as much as possible whilst also satisfying the thermal performance. Now, after careful consideration, investigation and material testing, the retention of the superstructure elements to 7 to 17 Whitcomb Street was rejected, as much as the original buildings had been altered in the development of the 1970s and 80s. The development 40 to 50 years ago created a building of poor construction. There's closely spaced column grid, low story heights, there's small windows, and there's ambiguous external areas that were put to no good use. We did review options to retain the existing structures and achieve the client's aspirations, but the interventions necessary both to the building and the vault would have been economically unfeasible, and we also would have been difficult to gain the relevant improvements from English Heritage and the planning conservation officers. Therefore, it was agreed within the team that any demolition spoil for these existing buildings would be sorted and graded on site and would be reused and recycled elsewhere. So the client's aspiration for differing building uses, maximise lettable area and the clear span floor plates, whilst working within the the existing listed structures as a significant change. Close collaboration with the design team early within the design process was key to ensure that the structural philosophies for the reuse of the existing structure could be agreed, and everyone understood the constraints and the limitations on what could be achieved. The structural design for the new development had to be carefully balanced against the capacity of the existing masonry structures in order to minimise intrusions into the basement and preserve its heritage. Therefore, the design considered approach to minimise material and any additional loading into the existing structure and foundations which might have caused failure. In addition to supporting the new buildings, and the spaces within the existing structures were also restored to accommodate new gallery spaces, offices and retail areas. And within the basement, dry ice blasting was used in lieu of grit blasting, chemical or mechanical means. And this innovative method had less environmental impacts. It removed the paint and dirt quickly and effectively and avoided damage to the structure below. And due to it being a dry process, avoided sand and water within the basement, which sped up any cleaning activities. So in addition to reusing and restoring the existing listed vaults, we also created new basement areas adjacent to the existing, which extended the basement and allowed for the alignment of the facades around down Wickham Street, improving the streetscape. The new structure also allowed the alignment of the pedestrian access across the site to improve permeability of the area, and it also allowed access into the new courtyard area and the restored vaults, which could only be previously accessed down a small staircase within Suffolk Street. A ground floor reinforced concrete transfer grillage was developed to evenly spread the weight of the new building over the vaults within 717 Whitcomb Street into the existing masonry walls and foundations. It also enabled us to provide step-free access into the ground floor retail units, which was not previously available with the existing buildings. Structural zones to the floors and walls were minimised, not only to eliminate story heights and maximise internal spaces, also to reduce and minimise material within the floors and facades. The slim floor system that fit within the structural slab depth, utilising fabricated shallow beams and utilising the plug composite action, enabled a very compact structural zone whilst achieving up to 9.5 metre clear spans, meeting market demand for open areas with substantial floor-to-ceiling heights. Concrete with a high level of cement replacement, up to 80% GGBS, was written into the specification for newly constructed elements, not reliant on the early strength gain, such as within the foundation works. You know, as we didn't need to prop the concrete slabs on metal deck, we also used similar philosophy, but we also included the use of lightweight recycled aggregate within all areas, with the exception of the residential areas due to acoustic reasons. So the facade for the new build elements typically featured handset bricks and punched windows. So bricks were selected due to the location of the project and the relationships with surrounding building typologies and the conservation areas, but also bricks have a lower embodied carbon system. So as the building rises, the brick cladding moves to a faceted shape with many different angles, minimising the massing on the streetscape and allowing pedestrians to see more of the sky. Facets also allow the windows to project out from the facade, expanding the internal spaces. And the main challenges with the inclined brick walls, their interfaces with the projecting windows and the high thermal performance requirements. And when considered in conjunction with the target floor areas, this drove the design to utilise a highly engineered facade build-up, which overlapped the skill of structural engineers with those of facade engineering in order to achieve the geometry and to compress the wall build-up. So closely spaced perimeter columns were cranked to allow for the faceted shape, and it avoided the inset boxing out, which would have disrupted the floor plate. Also, the strategy thinned the overall facade wall build-up as the loading could be for a number of columns. The use of prefabricated structurally insulated panels as the relief contributed to the load carrying system for the faceted handset brick facade, but also its thermal performance. And although structurally insulated panels have a high embodied carbon as an individual element, when compared with alternative facade systems that have multiple layers, the SIPs have a lower overall embodied carbon as a facade arrangement. Used in conjunction with the closely spaced columns, it avoided additional framing elements to support the inclined brickwork, decreased the thickness of the facade, and removed any additional coordination, saving time. So this is what the existing basement used to look like in 2013. Bit horrible. After its restoration, it now back to its full beauty and glory. In a similar manner to the buildings, as you can see, these are the existing buildings, small windows, very, ambiguous external spaces, but again, this is what stands there in Whitcomb Street today. These actions, as well as a number of others by the team, as a combined effort, achieved the BREEAM Excellent rating. And whilst benchmarking on embodied carbon was not commonly published in 2013 when the project was conceived, our steps to achieve a low embodied carbon building are clear. And using TT's carbon calculator, we measured the embodied carbon of the structure at about 375 kilograms of embodied carbon per metre squared, with an overall figure of about 495 kilograms of CO2 per metre squared. Now that we have the benchmarking available from LETI, we can show the benefit of our foresight, and we delivered a building approximately 10 years ahead of the proposed 2020 target. Our last example is a new 4-storey office development for a major bank in the northwest of England. Now, as with the tower in the City of London, the client had high aspirations, not only for a low embodied carbon building, but also a building that created a positive environment for its staff. Understanding this at the inception of the project, we were able to work with the team to ensure all these could be addressed. The requirement for this healthy building was instilled from the outset. The team strived to achieve WELL certification, creating positive spaces with exposed structure, natural light, natural ventilation, and foliage amongst some of the measures implemented. In working through the proposals, a hybrid steel frame with cross-laminated timber floors had been detailed to create flexible internal spaces alongside its sustainable and wellness credentials. The initial principles from the outset was how repetition and efficiencies could be incorporated within the design to allow the structure to be assembled from effectively a kit of parts. These philosophies were considered for end of life as well, whereby the structure could be dismantled piece by piece to be reused or recycled. In the original scheme, there was a large multi-storey car park for staff constructed next door to the office building. And envisaging that vehicle usage may decrease within the future, we looked at options as to how this structure could be adapted for other uses and to avoid its demolition and subsequent reconstruction. So the thoughts of a healthy build and the staff using it was highly important to the client. The story on how the staff would get to their desks from their cars using the spaces along the way was consistently run by the architect and the design team to ensure that the spaces responded in a positive way to the staff working there. The campus type working environment includes for a nursery, health club and bank on site, while the boulevard down the centre of the building contains other amenity spaces to create a vibrant community feel. From this boulevard, you can access the upper floor levels by sweeping staircases up the building. Now, understanding what was important to all parties, we worked with the architects and clients to develop the structural proposal. And in a similar manner to the tower in the City of London, the global warming potential of each structural solution was assessed alongside all the other aspirations. And although a full timber option provided the lowest figure, the hybrid steel and timber scheme was selected due to the minimum structural zone it presented, which in turn would reduce the building height and the facade extent. So unlike the high-rise tower, the requirement for large clear spans were not required in this building, and the proposed 9 by 9 metre grid was optimal for this type of system, especially under the vibration cases as discussed previously. The simplicity and the repetition of this structural system allows for efficiencies and economies of scale, allowing for this kit of parts to arrive to site to be assembled. And in utilising the repetition design, we could also focus our energy in optimising the structure to its full potential. So, looking at the car park and envisaging that the car park usage may decrease in the future, we proposed the structures of the car accommodate changes. So instead of demolishing the structure and reconstructing something else in its place, could it be easily adaptable to something else like residential units or increase the office areas? So therefore we did comparisons between the column grids of the offices and the car park to see whether we could do any subtle tweaks and allow for a flexible layout. to ensure that we got the car parking arrangements that we could achieve, and working with the 1500 raised access floor grid you generally find within office, we proposed a grid which would work for both a full precast solution or a steel solution. Now, as the imposed loading requirements between offices and car parks are similar, the extra over association allowance for loading associated with finishes, services and partitions had to be considered, but was deemed to have minimal effect on the overall structural design. Now, there are obvious challenges with this, such as the different story heights between an office and a car park. You know, could we remove intermittent stories and reuse elsewhere? Also, we had to look at what repair works would be necessary when the structure when we changed it from a sheltered external structure to an enclosed internal space. And also, how do you convince, or just, you know, the client, do they want to spend this money up front to allow for flexibility within the design, which may not ever be realised in the final case? Unfortunately, I can't give you all the answers to those, as this scheme was amended to remove the multi-storey car parks, but it's something to think about within your own time. And again, using our carbon calculator, we measured the embodied carbon of this structure between about 170 and 200 kilograms of embodied carbon per metre squared. And again, what we can show is that based on the benchmarking from Reba and Letty, we can deliver a building about 15 to 20 years ahead of the proposed 2020 targets. So, as shown from our examples, low embodied carbon structures need to be balanced within the brief and the overall requirements of the project. The selection of a particular option may have an effect on something else in the building, such as the building height, the facade build-up, or the service strategy. So, close collaboration with the design team, the client, is key to ensure that the aspirations of the project can be met. And this may involve educating the team as to why designs are completed in a particular manner and what is reasonably achievable. So, as structural engineers, we shouldn't be scared in challenging the designs of others in order to seek an optimum solution. We shouldn't take these designs as the final solution. We should be striving to make a difference, questioning proposals and decisions, and presenting options that could enhance or better the designs, better the designs in terms of the sustainable credentials. So our actions during the design process need to be followed through into construction. So the relationships with contractors and their supply chains are critical. It's important to engage with contractors early in the design process to understand the buildability issues, ensuring what has been specified can be procured and what can be achieved on site to ensure and fulfill the aspirations of the team. So based upon the above, we must understand where the opportunities are in order to design and construct buildings to reduce embodied carbon. There's a large amount of research and development going on, not only to drive sustainable technologies, but to also understand the data to fully understand how and where we should be optimizing our designs. Now, tools can be used to evaluate our designs during the inception of projects. However, we should be taking a step back to answer some of the key questions, as we stated before starting the design process. Can we reuse buildings instead of demolish them? Can we gain efficiencies and economies in scale with repetition? Can we optimize our designs to minimize material? Can we provide flexibility in our designs for future building reuse? Can we challenge the proposals and drive the structural design to achieve the desired outcomes? We never counted carbon on HOBHOUSE during the design process. It was only afterwards that, when we were running through the data, we understand what we had accomplished, showing that just designing in a correct and efficient manner can have a huge impact. So going back to our original question, what is the structural sweet spot for optimizing materials in order to reduce embodied carbon? And are there rules of thumb that designers can use for optimization, or does it occur on a case-by-case basis? As we've said before, unfortunately, there isn't a one-size-fits-all solution. Every project is different, as we've shown within our examples we presented earlier. However, principles and the philosophies taken for each are very similar and relate to all the items listed out above. Personally, I think we should be looking at addressing all of these items during the design process. Only then will we be able to optimize the design in order to reduce our embodied carbon. Thank you.
Great. Thank you so much, Simon and Duncan. We are right at the very end of our 45 minutes, but I think the questions that came in were hopefully answered in your conclusions there. But if not, we'll ask you to answer those and we'll post them on the CarbonPositive website. So for all the attendees, thank you. We will hopefully see you on following sessions, which again, you can find on the agenda page of the CarbonPositive website. And a reminder also, if you want to learn more about Beacon, to join the tool tutorial at 5:30, which Duncan will be putting on. All right, thank you all.
Thank you.